yeah. So we have some more space telescopes. I'm, of course, Joe Karowski, and that's Savannah. And just a little timeline of what happened and if they're still active or not. So Hubble, of course, 1990, and is still active. Chandra, 1999, still active. Spitzer, launched in 2003, and its deactivation was January 30. Oh,
They're
that's
planning
its
on
plan.
deactivating it
Oh, that's right.
end of January.
And then because James Webb is sort of currently still in development, but we're still just going to add that because it's eventually going to replace the Hubble if it is what it is. So I'm going to tell you a little bit about the Hubble. So, of course, it was named after Edwin Hubble, and then launched in April 24th, 1990. Entered service in May 20th, 1990, and it's about the size of a school bus. Pretty big. And then it was oh my gosh.
$1 billion mistake.
Ever since you told me about this last year, I've been wrapped up on it. The $1 billion mistake. So I'm just gonna quickly compare. This is kind of what the first picture was.
We've got better.
Yeah, there's other ones, but
This is the difference between taking a picture from the ground and taking a
Yeah.
picture out in
Yeah.
space.
oh, okay. So there's that comparison, and then
That's why we want a telescope orbiting instead of having atmospheric interference.
Yeah.
This is your performance.
there. This is yeah. So this is supposed to be the first picture, but instead we ended up getting this one as our first Hubble picture, and everybody was like, "What the heck? We spend like a bunch of money on this only to get like a blurry picture." That's like for all the photographers in this building. It's like taking a really nice photo of the sunset only to get like that weird red smudge on the screen, and it's just
You got it? Oh, help me.
Oh my. Yes.
Go. What kind of that up?
popcorn,
All
popcorn.
kernels that hit the floor will be picked up and hit the garbage can.
Will be
Yes.
from your face.
But
Yeah, I get it.
But so, yeah, so basically what we figured out was the Hubble kind of had nearsightedness. Well, I have the opposite. I have,
Oh, yeah. Oh, the lens or something.
yep, the lens.
Okay.
So basically, it's about as thin as the strand of hair the lens was, and so we had to put contacts on the poor thing. So then we could finally get this one.
How
So,
did they get a contact on it though? They send somebody else up there or what?
well, I think it was it
Space
just,
shuttle.
yeah, space shuttle. Small little mission. So, yeah.
It was flawed. So when they were grinding the lens, it was flattened out too much on the edges.
By less than a human hair.
It was super tiny, but you can see the huge difference. And essentially, they gave Hubble glasses,
Yeah.
which is rather hilarious
cool.
when you think about it.
But thankfully we did that so then we could get the two cool ones. So there's, of course, the pillars. I always say it's the pillars of life, but it's technically called
Pillars
the
of creation.
pillars of creation. So I can't remember which nebula.
Eagle.
Eagle Nebula, where we found that, and basically this is all gas, and I can't remember which gases it was.
Gas and dust.
Gas and dust, and apparently this is sort of like, well, I shouldn't say apparently, it has been proven that this is where stars, this is where stars really do come from, and, you know, stars.
Foreshadowing to next week.
Yes.
Oh, that's right, I was almost about to give it away, thank you for reminding me. And, of course, because my favorite color is red, Proxima Centauri. That was a really cool picture that you found. Of course, when we were talking about Halloween, there's the space, or,
Galactic cannibalism.
galactic cannibalism, and, let's see, where's the deep field? Okay, so this is the deep field. So this is like a huge collage of like there's galaxies and stars and
Thousands of galaxies.
thousands of them.
Super cool.
And I can't remember when they took it, but they were just like, let's just
1996.
We've got a video
Nice.
that explains it.
yeah.
Very.
And so, yep, the cosmic face, and then bottom left, yep, the farthest galaxy ever took in a picture of, right there.
Distant galaxy.
Yes. And then here's that video.
Astronomers in 1996 attempted to do something extraordinary. They pointed the Hubble Space Telescope into a part of the sky that seemed utterly empty, a patch devoid of any planets, stars, and galaxies. This area was close to the Big Dipper, a very familiar constellation, and the patch of sky was no bigger than a grain of sand held out at arm's length. This was a somewhat risky move by the scientists. After all, observing time on this telescope is in very high demand, and some questioned whether it would be wasted trying to look at nothing. There was a real risk that the images returned would be as black as the space at which it was being pointed. Nevertheless, they opened the telescope and slowly, over the course of 10 full days, photons that had been traveling for over 13 billion years finally ended their journey on the detector of humanity's most powerful telescope. Their feeble signals collected almost one by one. When the telescope was finally closed and the images were processed, the light from over 3,000 galaxies had covered the detector, producing one of the most profound and humbling images in all of human history. Every single spot, smear, and dot was an entire galaxy, and each one containing hundreds of billions of stars. Later, in 2004, they did it again, this time pointing the telescope towards an area near the constellation Orion. They opened the shutter for over 11 days and 400 complete orbits around the Earth. Using detectors with increased sensitivity and filters that allowed more light through than ever before, over 10,000 galaxies appeared in what became known as the Ultra Deep Field, an image that represented the farthest we've ever seen into the universe. The photons from these galaxies left when the universe was only 500 million years old, and 13 billion years later, they end their long journey as a small blip on a telescope CCD. These galaxies, while standing absolutely still, are racing away from us, in some cases, faster than the speed of light. The space-time between us and everything else grows larger by the minute, pushing the galaxies in this image to a distance of over 47 billion light years. And because of universal expansion, the farther something is away from us, the more its light is shifted toward the red, and the faster it appears to be moving. Edwin Hubble himself discovered this by measuring the redshift of many galaxies, and it's a measure of not only speed, but distance as well. Recently, Hubble scientists put the icing on the cake. Using the measured redshifts of all the galaxies inside the image, they made a 3D model of the ultra-deep field. This is how it looks when we apply the distances of the galaxies in the most important image ever taken. There are over 100 billion galaxies in the universe. Simply saying that number doesn't really mean much to us because it doesn't provide any context. Our brains have no way to accurately put that in any meaningful perspective. When we look at this image, however, and think about the context of how it was made, and really understand what it means, we instantly gain the perspective and cannot help but be forever changed by it. We pointed the most powerful telescope ever built by human beings at absolutely nothing, for no other reason than because we were curious, and discovered that we occupy a very tiny place in the heavens.
So yeah,
Hard to follow that up.
yeah, with poor Chandra.
Yeah.
Poor thing. I mean, there's a cool one. But yeah, it launched in July 23rd, 1999, and it was designed to view the universe with X-rays. You know, not like the normal stuff that the doctor uses on you. Cool ones. So, and it helps see black holes, quasars, and supernovas from far away and close, and also added evidence to the dark matter and energy theories. Oh, that's right, it was 54, like, feet or inches long. Yep, feet long. I forgot to add that. And so,
These are a couple of really cool pictures, and then this is the black hole that they had a picture of earlier this year. So kind of
So this is what they do is they measure x-rays and then they assign colors so
Yep.
that we can see what it is.
which is super cool.
you got Spitzer.
Spitzer. All right, so it was launched August 23rd, 2003, and then it entered service December 18th of that year, and then planning on deactivating it, sadly, in the end of January next year. And it was only supposed to work
Next
for
year?
2021. And then it was only supposed to work for 2.5 years, which is rather short, but it's exceeded that lifespan. So Sean reviewed everything in X-rays, and Spitzer was designed to view everything in infrared. So these are a couple of really cool pictures, and then that is the goal. I don't remember what that one is, but we covered it. Galactic.
Gravitational lensing.
Yes.
Because there's the, not Lagrange, but
Those are galaxies that are well beyond
oh, the
the
shiny,
foreground.
yeah, the shiny things, but you could see like this
The,
little line right here.
Yeah.
That's
Those
what
are
I was
galaxies that are well beyond what's in the foreground.
Okay, so
So there's something massive gravitationally that's causing the light to bend.
which is really cool that we can see
So
that.
this is dark matter evidence.
Yep, that's the dark matter.
Yeah, these are some pretty cool pictures. All right, this is my favorite of all of these, the James Webb, and it was named after a former NASA administrator. They're planning on launching it March 30th, 2021, so it's not too far off.
Fingers crossed.
Yeah. It is a really, really cool version of Hubble. So it's essentially Hubble on steroids in a way, which it's supposed to replace Hubble, and then it, fingers crossed, should be able to study how stars and planets form. So we should be able to see that in.
And all these yellow panels, aren't they like mirrors?
Yes, they are mirrors that we can see stuff with. So it's,
Yeah, they're like
I don't know.
6 meters across or something.
They are huge. I have a video explaining all of it,
Excellent.
which is amazing.
Ridiculous.
So, SciShow.
You'll get no arguments from me. The Hubble Space Telescope is fantastic, but it's not fantastic at everything. In fact, it and nearly every other telescope is crap at detecting most of the infrared wavelengths of light. The Hubble can detect the near infrared, the shortest wavelengths of IR that are closest to visible light, but the real juicy goodness is in the mid-infrared wavelengths that are impossible to capture from most places on Earth, and still hard as heck to detect in space. Now, if you tried to scale up the Hubble's mirror to work in that range, it would be 1. Larger in diameter than the biggest rockets that currently exist in order to collect enough light, 2. Maddeningly difficult, if not impossible, to accurately polish, 3. Deformed beyond usability at the extremely low temperatures necessary to see IR light, 4. Too heavy to launch, and 5, worst of all, still unable to reflect light at the infrared range. So yeah, there's a reason people said that building a high-resolution IR telescope was impossible. Actually, 5 reasons that we just discussed. But it is possible, because we've built this mirror. We've taken each of those challenges on, and remarkably, we're finished. Now it's just a matter of waiting for the rest of the James Webb Space Telescope to be completed and sent into deep space to start taking pretty pictures. Well, let's take a look at those 5 big problems, and with the help of Northrop Grumman's Scott Willoughby, determine how we overcame each of them. First, the vehicle used to launch the Webb into space, the Ariane 5 rocket, has a diameter of 5.5 meters. And the Webb's telescope meter has a diameter of about 6.5 meters. And that's not even mentioning that it would be impossible to polish a mirror that big, so yeah, problematic. Solution, build your mirror in 18 foldable pieces.
The reason we built those in 18 segments instead of 1, I was mentioning there was 2 reasons. One is we basically couldn't polish a mirror that big, and then the other thing is we had to segment it so we could put 3 and 3 on a hinge one.
As the telescope travels to its destination, these mirrors will fold out. In fact, the whole thing will transform out of its little cocoon into the beautiful butterfly that it was meant to be. Hot stuff, problem number 1 and number 2, solved. Now, Number 3. How do you make a mirror on Earth that will work in deep space? First, you use beryllium.
Beryllium was chosen because at these cold temperatures, it holds its shape, basically precisely. You can't afford to have this be moving around.
But it's more than that. They have to anticipate how the mirrors will deform at 40 degrees above absolute zero. They actually only finished the prescription of the mirror, just like the prescription in my glasses, after bringing the mirror down to negative 387 degrees Fahrenheit to see what its shape will be.
It would be blurry at room temperature, so when it goes down to 40 degrees above absolute zero, it crisps up.
Still, beryllium, though fantastic in cold temperatures, is way too heavy to launch. So now we must solve problem number 4, how to be lighter per square meter than Hubble's mirror. Well, hollow the sucker out.
I think the block is about 400 pounds, and it ends up being about 40 pounds. It's a very thin face sheet, and if you looked at the back of it, it's basically a grid of ribs. One piece of metal that gets basically hogged out by a machine.
And finally, how do you get it to reflect infrared when beryllium is crap at even being